In this video, we want to get some practice with bicyclic nomenclature. And to do that, we'll follow the four-step procedure. ID the parent, count the carbons along each bridge, ID the substituents, and then arrange everything alphabetically. So let's look at the parent chain for this first molecule. We're going to count all of the carbons that make up that bicyclic structure. So 1, 2, 3, 4, 5, 6, 7, 8. And so we have bicyclooctane. Then we want to count the carbons along each bridge, and I'm going to use a different color here. Let's identify the bridgehead carbons with the red dot, and we want to count how many carbons connect those two red dots, and there should be 3 different numbers that we're looking for. So here's 1, 2, 3. 1, 2, and 1. And so then we will prepare the brackets with those numbers in numerical order. 1, 3, 2, 1. And we'll use the decimal points to separate those numbers. And then I'm going to number this so that I can ID the substituents and give them a locant. And I'm going to start my numbering at one of those red dotted carbons. I'm going to choose this one for number 1 because it has a substituent, and that will give the isopropyl group the lowest possible number. And then we're going to number following the longest bridge. If there's a choice between longest bridges, we'll number so that the next substituent gets the lowest number. So in this case, we don't have a choice. We have to go this way. And the other bridgehead carbon then gets to be carbon number 5, and we keep numbering around until we come back to the original bridgehead, and then if we have carbons that are left over, like we do here, that gets an 8, and that's going to be not connected to the 7, but that's okay. Now I'm going to write out the substituents. I have a 1 isopropyl, and I have a 3, 3, 8, 8 tetramethyl. And I believe, if I go back and look at my molecule, that is all I have regarding substituents. So now it's time to put the whole name together. I'm going to alphabetize. I comes before M, so we'll use 1 isopropyl first. And then I have 3, 3, 8, 8 tetramethyl. And then I have bicyclo. And here's where I put my numbers in, 3, 2, 1, octane. And that would be the proper IUPAC name for this molecule. Let's take a look at the second molecule. In this case, I have to ID the parent chain. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 carbons. This would be bicyclo nonane. And I'm going to again identify the bridgehead carbons, and I'm going to come up with my 3 numbers in brackets. And in this case, I have 1, 2, 3, 4, 1, 2, 3, and this is the tricky part. I have a 0. There are no carbons between these 2 bridgehead carbons when I follow this pathway. So I have a 4, a 3, and a 0. And here I will show you a little way to check your numbering. Up here we had an octane that has 8 carbons. These numbers added to 6 because I wasn't counting the 2 bridgehead carbons. So your numbers should always add up to 2 less than however long your parent chain is. Here I have a nonane, that's 9. These numbers add up to 7. That makes sense because I didn't include these in my bridging carbon count. So 430, 0 is a perfectly reasonable number to have in this case. Now we need to ID the substituents, and I'm going to number this molecule along the parent chain. I'm going to start right here with one of those bridgehead carbons that has a substituent, and then I'm going to number along the next, the longest bridge. And you'll notice that I did not start numbering closer to the dimethyl arrangement here. I had to go this way because it was next to the 1. And so the dimethyls might have been happier with a 2,2 dimethyl, but I was forced to make them a 5,5 dimethyl. And so now I can put my substituents together, and I have a 1-T-butyl, and I have 5,5,7-trimethyl. And those are all the substituents I have, so we can put this in order. Let's see, the butyl comes before methyl, so I'm actually just going to use the T-butyl as written there and extend it with 5,5,7-trimethyl. And then I add the bicyclo, brackets 4, 3, 0, nonane. And that would be the complete name for this bicyclic structure. Incidentally, the reason it's called bicyclic is because it takes at least 2 bond cleavages, cutting 2 bonds to make the molecule totally non-cyclic. And we can observe that with any 2 bonds here. If I cut the bond between 7 and 8, I still have this ring over here. So I need to cut another bond, maybe between 4 and 5, in order to have a molecule that would have no rings in it. And that's where we get the bicyclic structure from, if you're curious about that. Moving on to the third example. I got my 2 bridgeheads here. I'm going to count 1, 2, 3, 4, 5, 6. So this is bicyclononane. Hexane, I mean, not nonane. And then I can count my bridging carbons. I have a 1 here, I have a 1 here, and I have 2 right there. So I would have 2, 1, 1. Again, this adds up to 4. It is 2 less than hexane, so I can double check my counting there. Let's number this according to IUPAC rules. I'm going to start with this bridgehead because it has a substituent, and I'll number along the longest bridge, which is this one containing the chlorine. The other bridgehead gets number 4. And now I have a choice for the next longest bridge, and I could go up or across to the left. And I'm going to go to left because that will give my methyls a smaller number. And then 6 gets there at the top. So I have a 2-chloro, and I have a 1, 5, 5 trimethyl. And the chloro comes before trimethyl, so I'm going to just use the 2-chloro, 1, 5, 5 trimethyl, bicyclo, 2, 1, 1 hexane, not octane. I don't know why I'm stuck on octane. And that would be the proper IUPAC name for this bicyclic structure.